So for electrophilic aromatic substitution, you know that something like this methoxy group, is an electron donating group and therefore a ortho-para-director. But why does that make it an ortho-para-director? Now this is how I was taught to think about it. Okay, and there's a couple other ways you can show to prove. This is how I was taught to think about it and what helps me. So we have our methoxy group that has these lone pairs that it can donate down into the ring. Remember, it's an activating group. It primes that ring for EAS. So we're going to donate these electrons down into our ring. Now we can't have 5 bonds on a carbon here. So we gotta kick these electrons up over here. And this is what we get. We get this lone pair sitting right at the ortho position. So there's extra electron density there. Now we can kick this lone pair down here, but then we gotta kick this pi bond over here, which gives us a lone pair at the para position. I forgot to put an arrow here. We can do it again. Kick our electrons right here, but then we got to kick this pi bond back up. Kick it right here, and we get the pi bond back at the ortho position. Again, just on the other side, the other ortho position. And then what we can do to just kind of undo it all is we can kick the electrons here, we kick this back up onto our oxygen, and we're back to our original methoxybenzene. This is how I was taught to think about ortho-para-directors. When you donate electrons down into the ring and start pushing around electrons and pi bonds, you always end up with extra electrons at the ortho and para positions.